Good evening. We will continue multivariate linear regression, and now we will discuss about model adequacy test for multivariate linear regression, the model adequacy test. If you recollect multiple linear regression, so we have considered R square, RA square. We have also developed one table called ANOVA table for F test, correct. And what we have done, basically we have set certain hypothesis. That hypothesis is beta j equal to 0 for all j equal to 1 to p, and we created alternate hypothesis that beta j not equal to 0 for at least 1 xj. That was the hypothesis we have tested, and we have used this ANOVA table like this. Okay. In addition, what we have done also, while preparing the ANOVA table, we have found out that the total sum square or sum square total we divided or partitioned into two half, that is SSR plus SSE. That means the total or sum square total equal to sum square regressions then sum square residuals or sum square errors, correct. And using this, then degree of freedom was n minus 1, then here p plus n minus p minus 1. Okay. So, this one, in addition to this is basically all our model fitting. Coming to model fitting, in addition to this we have test of assumptions. That means we have done normality test, equal variance test, linearity test. We have also tested for autocorrelated errors, autocorrelation test. You can remember this. In addition, we also have done something called model diagnostics. That is basically coming under residual plots. And in multiple regression you find out that several residuals, different types of residuals, like your studentage residuals, praise residuals or deleted residuals, then there was a standardized residual, then we have seen that ultimately Cook's distance, then your d fits, d betas, so many things are there which are for finding out the leverage points, outliers, leverage points as well as outliers. Ultimately we say these are all influential observations. So, can all those things not be done in MVLR? You are getting me? It is possible, and most of the times the software will give you the outputs. Suppose SPSS, Minitab, SAS, CSTAT, Statistica, whatever software you use, ultimately you will get these outputs. Okay. So, we will see some analog from MLR to MVLR, that means multivariate linear regression. And if you do little more imagination, then what you will find out that it is just MLR. If it is related to ANOVA, then MLR is similar to MANOVA. Getting me? So, now let us see that in MVLR how do we get that F test R square, R A square, similar thing, and how do we partition the matrix? That matrix is that total sum square cross product matrix, all those things. And what about the test of error assumptions? This is the in totality we will be discussing within this 1 hour or 50 minutes of time. Okay. So, then let us write down again in the last class what we have written, and so that you can correlate with this. We say this is n cross q, where n is the number of observations, q is the number of dependent variables. Then we say this one is our n cross p plus 1. So, our p is number of IVs, and your beta is your p plus 1 cross q. Okay. So, now what is q? Q is number of DVs, then this one is n cross q. Okay. So, this equation will be using, and once you have estimate that y cap, this is your x beta cap, and also we know that epsilon cap is y minus y cap. These are the few things we have discussed earlier, and these things will be required. So, what we will do with these things? Suppose I want to know y transpose y. Getting me? I want to know y transpose y. What will be this? This will be x beta plus this transpose into x beta this, because we are writing same equation, that this transpose this into this. Okay. Now, if I write y cap transpose y cap, then this is nothing but x beta cap transpose x beta cap. Similarly, I can write this transpose epsilon cap, which is nothing but y minus y cap transpose y minus y cap. Okay. Now, I want to know what is this y transpose y. What is y? Y is n cross q. Then what is your transpose? Q cross n. Correct? Then this one, if I write like this, some matrix you will be getting which is q cross q. Similarly, here you see this is again q cross n, n cross q. You will also be getting some matrix here of q cross q. Here this one is also q cross n, n cross q. You will be getting something here q cross q. So, if I say this is my SSCP total, which is a q cross q matrix, this is my SSCP y cap, that is basically what is the that regression point of view, how much we are getting. This is also equivalent. If I say this one is like this epsilon, if I write like this, or cap. Okay. So, see, you will find out in MLR what we have found out. We found out SST equal to SSR plus SSE Similarly, here we can write like this: SSCP total equal to SSCP your y cap plus SSCP epsilon cap. Can you find any relationship with this with MANOVA? In MANOVA we have found out that SSCP total equal to SSCP between plus SSCP error within. In MANOVA we have used suppose T SSCP total equal to error between SSCP between plus SSCP error. So, because of q variable y variables your now matrix becomes like this. Suppose I want to create R square. Can I create R square here in the same manner here? R square is what? SS R by SST, that is from MLR point of view. But you will not get here because these are all in the matrix domain. But in MANOVA what we have done, we created one Wilks lambda, that one we say what is SSCP I think E divided by SSCP total. So, this is what is the likelihood ratio test. Now, can we get similar measure here in your multivariate linear regression case or not? Okay. So, yes, here in multivariate linear regression also we will go for likelihood ratio test, and here that R square like measures just exactly 1 to 1, that type of relationship is not possible. But yes, there are some other measures which basically were derived based on that F ratio, F statistics point of view, that what is this MSR by MSE. In R square ANOVA table you found out that F equal to MSR by MSE. So, MSR minus F MSE, this equal to 0. So, this type of relationship can be used and we will find out some measures with respect to this. Okay. So, in this context let me show you this slide. In this slide you see this for Y1, that is profit, this is for sales, these are residuals, getting me, residuals. So, how many y variable, 2 y variable. So, what will be the q cross q, 2 cross 2. So, this data can be used because this is epsilon cap, this data can be used to find out this 2 cross 2 that SSCP matrix. Now, what is this one? This is the predicted one which is y cap. So, predicted one, this predicted one when subtracted from the actual y value you have got this residual. So, this can be used to find out this SSCP y. Now, SSCP y will be SSCP y cap plus SSCP epsilon cap. So, repeat this fitted values will be used to find out SSCP y cap. This will be used to find out SSCP cap, and already y values are there, but you can check also using this formulation. Okay. So, in this example our Q is to show all SSCP total, that will be 2 cross 2 equal to SSCP y cap, that will be 2 cross 2 plus SSCP epsilon cap, that will be 2 cross 2. So, it is similar to your SST equal to SSR plus SSE. Okay. So, difference is this is the matrix domain, scalar, okay, vector and scalar domain, basically matrix. Okay, fine. We will do some tests. The test is basically that what I can say here, a general test, that is what I can say, that generalized hypothesis testing, generalized hypothesis, in the sense you have X data matrix and which is basically your P plus 1 n cross P plus 1. So, your beta is there, this vector beta vector, which is how many beta is P plus 1 cross Q, correct, and your y variable. So, if I go by variable only, so if I go by variable, y is having Q cross 1 variable, x is having your, including the constant, I can say P plus 1 cross 1 variable, including constant is there. Okay. Now, you may be, so if I write down here for the y variable, q 1 variable case, so the beta part I can write like this, beta is beta 0, beta 1, beta 2, beta q will write, no, we will write like this, beta 1 to beta q. Okay. Now, this beta 0 contains P plus 1 into 1, this also contain beta 2 also contain P plus 1 cross 1, like this. Okay. So, this, that is why it is P plus 1 cross Q, fine. Now, I and your what I will do here, I will say that sum of the variables, independent variables are not contributing. Instead of writing that the jth variable is not contributing, I am saying, or we are trying to find out that sum of the independent variables are not contributing. Getting me? Subset of P plus P variables, constant always is there, subset of P variables are not contributing towards explaining the y variability. So, here you have P plus 1, P plus 1, P plus 1. If I say that this one is starting from this, that is P plus 1 minus m up to this, then this one is m, because total is P plus 1. So, we are trying to say that this P plus 1 minus m, this many variables are contributing, and then remaining m variables are not contributing. Instead of writing that the particular beta k variable is not contributing or beta j variable is not contributing, what you are doing here? You are simply saying that a subset of variable is not contributing. Getting me? If this is the case, so what I am then trying to say? I am trying to say that I am creating two sets. This one is your x0, this one we are writing like x within bracket m. Getting me? So, that means I have total P plus 1 including constant p plus 1. So, under H0, that is the null hypothesis H0, what we are saying that beta m, getting me? We are basically trying to say beta m which is equal to your that beta, this one is p plus 1 minus m. So, that means p plus 1 minus m plus 1. So, p minus m to beta p. I have beta 0 to beta p. I am taking the last m not contributing. So, that means p to p minus m. So, this is 0. This is 0. So, please understand what we are trying to say. We are trying to say there are p variables, let it be 20, p equal to 20. So, I am saying that that 15 variables are contributing, 5 variables as a whole they are not contributing. So, I can rearrange those variables, first 15 variable contributing like this p plus 1 minus m, that x 0, and last is not contributing x m. We can write like this. So, here also we are writing x 0 within bracket, so that it will not be confused with x 0, that constant, correct. Then H 1 is here, that beta m not equal to 0 for at least one of the variable, for at least one beta m j. Okay. That means the remaining the variables what you are discarding, they are not to be discarded, they are also contributing. Okay. So, then under such situation, if I want to write down what is the expected value of y, this is nothing but expected value of x beta plus epsilon, which is nothing but expected value of x beta. The reason is expected value of epsilon, that is basically 0, and ultimately this lead to x beta only. Okay. So, if you write this one like this, that x 0 then x m, x 0 and x m, x 0 p plus 1, what is this? This one is n into p plus 1 minus m, and this one is n into m. Clear? So, then same thing I can write for beta, beta 0, beta m. And what is this beta 0? This is definitely p plus 1 minus m cross q, and this one is your only that how many m cross q. The resultant will be basically this will be m cross q and this cross q, like this. Okay. So, you can write down like this one, x 0 beta 0 plus x m beta m. We are not considering the error term because we have taken expected value of this. If m variables are not contributing towards explaining the y's variability, so that ultimately what will happen, beta m will 0. So, that means this resultant will be 0, getting me? Your x m beta m is basically beta p minus m, beta p minus m plus 1, like this, beta p, everything is 0. Whatever you, when you multiplied this into x p minus m xp minus m plus 1 and xp, this resultant quantity all also will become 0. So, what I am saying here that this quantity 0 means this expected value is dependent on this. We are using 0 to denote that under H0 this is the situation. Then under H0 our value will be, y will be x0 beta 0 plus epsilon. So, I can write like epsilon 0. See, this is under H0. If we say that beta m is contributing, then we will write the alternate one. Alternate is no, this beta m 0 you have considered that is false, which is basically x beta plus epsilon, what you have taken earlier. Getting me? So, what will happen here, if I fit this model vis-a-vis this model, you will be finding out SSCP epsilon 0 estimate here, and here also you will be finding out SSCP epsilon cap this estimate. Getting me? Now, if we as given by Johnson and Wichern in this book, I have seen that. So, if I say this is nothing but that estimate of this, or I can, you can straight away write 0, and this is nothing but this one estimate of this. Okay. This I have taken from Johnson and Wichern. You just check. So, what will happen then? One hand I have taken the total set of independent variables. In the other hand, what we have taken? We have said that H0 is true, that means m variables are not contributing. Getting me? If H0 is true, then the SSCP from the reduced model and SSCP from the full model will be same, the error term will be same. So, as a result, if I say under H1 this model is my full model and under H0 what is this model is reduced model, my question is that the error SSCP error, that matrix, that will be more or less equal. So, now if we create a ratio which is determinant of that full model SSCPE vis-a-vis your reduced model SSCPE, getting me? So, this ratio will vary, will stay in between 0 to 1. Okay. So, when it will become 0? Suppose obviously when I am going for full model, that this one it should be less than equal to should be, because in the reduced model you have eliminated many variables, their contribution you are not considering, that will come to the error term only SSCPE. So, obviously this now what will happen if this value is sufficiently small, sufficiently lower, okay, much lower than this value, it will be close to 0. If both are equal, it will be close to. Okay. So, if you find, what does it indicate? If you find out that lambda, that this lambda is known as Will's lambda, that in a MANOVA you have tested this. If this value is sufficiently close to 0, then what it is indicating? It is indicating that sigma capital sigma cap 0 is much more than the full model sigma cap. Getting me? So, as a result you reject H 0, but if it is equal to close to, it will not get 1, if it is close to 1, accept H 0. Getting me? Fine, but problem lies where? Problem lies this lambda, but the way you are making, these are all generalized variants. When you take the determinant of a variance covariance matrix, these are generalized variants, and this lambda is it is a point estimate. Getting me? Point estimate. What is the guarantee that this point estimate is giving you that what you want exactly? There is uncertainty. So, we require to know the interval estimates. So, as a result what is required? We require to know the distribution of what? Distribution of lambda. This is very important, correct? But lambda computation is complex. You see that so much of, first of all, SSCP matrix, that full model, reduced model, then if it is P is very large, Q is also large, then in that case what will happen? Complexity is huge. You cannot get straight cut the distribution for lambda, but researchers, particularly statisticians, they have worked on it and they found out that lambda in different transformation was made for Wilks lambda and some distributions were found out. The two important tests or distributions was given by, one is Bartlett, I think BARTLETT, Bartlett test, and another one is Bartlett test and Rao's test. These are all likelihood ratio test. So, what is Bartlett test? How do you compute Bartlett test? Bartlett test says that you create one statistics which is minus m log base E lambda log S B lambda. This is one statistic created where your m is a multiplier, m is the multiplier. This value is n minus p minus 1 minus q plus 1 minus m divided by 2. Okay. So, you know what is n? Total number of observations. What is p? Number of x variables. What is q? Number of y variables. What is m? That we are saying beta m under H0, beta m equal to 0. So, that m variables you have dropped, correct. So, under this condition, if you say this one, then these statistics, that means minus m log lambda, this follows F distribution, and also it follows chi-square distribution under certain conditions. So, chi-square distribution, that one is given by Bartlett. Yes, it can be approximated to F distribution also, but chi-square distribution, that m with mq degrees of freedom. So, m is number of variables dropped from the independent side, q is the number of y variables. So, this follows this distribution. Now what you will do then? You know that this chi-square distribution looks like this, and our this minus m log lambda, this follows chi-square distribution. So, for some value, that is the rejection region. So, you find out what is this value, is minus m log lambda is falling somewhere in the rejection region or not. So, this point, the critical value is your chi-square. If I say this is alpha, then chi-square mq alpha, this is your critical value. Now, you will reject H0 if minus m log lambda greater than equal to, you can write chi-square mq alpha. Okay. Now, second one is Rao's statistic. In 1952, Rao has given similar statistics for Wilks lambda. His statistics is this one, that the statistics what it created, it is 1 minus lambda to the power 1 by q divided by 1 by q into mq plus 1 minus mq by 2 divided by mq. This is the statistic. Okay. Where m already you have computed, m is the multiplier, earlier you have computed m. So, m we computed like this, this is our m. So, that m multiplier. What is q? Q is a quantity which is q square, small q square plus m square minus 4 divided by small q square plus m square minus 5 whole to the power half. This is given by Rao. Okay. So, please remember, if qm equal to 2, this quantity q becomes 0, capital Q becomes 0. If small q into m equal to 2, then q equal to capital Q equal to 0. Under such condition, you have to consider q equal to 1, unity. Other cases no problem, fine. So, you first find out these statistics. So, 1 minus lambda 1 by lambda to the power 1 by q by lambda to the power 1 by q, 1 by q. Okay. This is not y, this is 1 by q, mq plus 1 minus mq by 2 by mq. This quantity q will be computed like this. This follows a distribution with mq and capital M capital Q plus 1 minus mq by 2 degrees of freedom. So, what will be your, when you reject null hypothesis? If I say this statistics, this total value is d, then you reject H0 when d must be greater than equal to f mq m capital Q plus 1 minus mq by 2 into that one alpha value, this not into, this is the alpha probability value. Okay. So, when you are using this ratio, likelihood ratio statistics, these two statistics are useful, fine. So, when you, if you use SPSS, SAS or some other program like Minitab, you can ask Bartlett test, Rao test, but Bartlett test is available. Rao test, I do not think that Rao's test, I have not seen, it may be available. Okay. Now, question is, these tests are very sensible, in the sense, what I mean to say, for example, Bartlett's test. you say that chi-square distribution is followed, but chi-square distribution under what condition? It says that if your sample size is small, Bartlett test will not work. So, it says that n must be greater than p plus q plus 30. What is p? P is number of IVs, q is number of DVs, and 30 plus 30. This is the case. This one is basically developed by Sage Job, SCHAT ZOFF, SCHAT ZOFF in 1936, proved that for Bartlett test this is the requirement, then only the chi-square distribution will be followed. I think you understand. But there are other tests not based on likelihood ratio. Getting me? There are other tests which are not based on likelihood ratio test. These other tests are interestingly, suppose in ANOVA we know that F equal to MSR by MSE, that means MSR minus F MSE, this is 0, this is 0. Now, its equivalent or analog in multivariate domain. Okay. So, you all know that your multivariate domain you will not get this scalar, MSR, MSE all are scalar quantity in MLR, multiple linear regression, but MBLR you will not get this, you are getting SSCP matrix, and under H0 beta m equal to 0 we found out two things, that we said that under H0 you found out this SSCP and under full model you found out this one. Okay. Now, you can create one statistics which is basically R, similar to R I am using because of this regression. That means the regression this can be like this, you can create like this, R equal to this. That means what is this? This difference, how much the m variable you are dropping, that is contributing. You are testing H0 here also, in ANOVA also you test H0 here, and then you through F test you say yes, some of the variables are contributing, that is in MLR. But in MBLR also, if I say that what is this? This R is the difference between this and this multiplied by the number of observations, and if I say that E equal to N, that full model. Getting me? Now, I will, if I create like this, now what is happening? This R can be similar to MSE and E can be similar, R can be similar to MSR, E can be similar to MSE. But as they are in the matrix domain, they are equivalents in terms of your scalar domain, you have to take determinant. So, that is why what happened, that is statisticians have developed that if you take this determinant equal to 0, then you will get very interesting roots, characteristics. What is this? This is basically, if I write, it is nothing but n epsilon 0 cap sigma 0 cap minus sigma 0, that is R, minus lambda n sigma 0 sigma cap. This one, this is R minus lambda E, this is the matrix. Now, if I take determinant here, so ultimately what is happening, this n will go out, n will be cancelled because this you are putting is 0. So, this one is 0, this is the characteristics equation. getting me, and lambda will give you eigenvalues. That you know. Now this eigenvalue lambda, how many eigenvalues will be there? It all depend on the that what is this order, what is this order of this matrix, this resultant this matrix, that is what is the order of this matrix. We always think of the determinant mean full order, full rank matrix is required to be. Now suppose that we say that the order is basically S, which is minimum of Q and P minus M, that will be the order. Q is number of dependent variable, P is number of independent variable, M is number of dropout variables. So this is number of dropout variables. Okay. So then once you solve this equation R minus lambda E this equal to 0, you will be getting this will be S power, that power will be because there are S roots will be there. These roots are basically lambda 1 greater than equal to lambda 2 greater than equal to lambda S. These are the roots, and you will see that these roots when you do this eigenvalue decomposition of matrix similar this one. So that ultimately what you will find out? You will find out that P roots, or here it is S roots, and they will be that first root, first one is the maximum one followed by next mesh like this. Okay. So using this property, there are several statistics developed. Several statistics were developed. For example, you will find out that Wilks lambda will become like this. Wilks lambda will become like this, equal to this. This is nothing but determinant of E. I think E you can understand now the way we have defined, divided by E plus R. Are you getting some clue with MANOVA? Wilks lambda is SSCPE divided by SSCP between plus SSCPE. Now this between means what happened? Population contribution. So it is similar to regression contribution error. So that determinant of this divided by determinant of this we have computed there. So this one, when you define in terms of your eigenvalues, it will be like this: multiplication j equal to 1 to S 1 by 1 plus lambda j. Okay. So that means what you require to do, you require to find out this equation, then find out the lambda values, you will be able to find out this Wilks lambda values also, small lambda, capital lambda. This definitely follows certain distribution, and in all cases F distributions are approximated. Here some other distribution like chi-square, we have seen Bartlett has given chi-square distribution, Rao has given F distribution for this Wilks lambda. Apart from this, there is another statistics which is known as Pillai trace. Pillai trace statistics. What it is done? It takes V equal to trace of R into R plus E inverse. So these are just variant, almost similar under certain condition, but to get the different benefits it is done like this, and this one will become j equal to 1 to S lambda j by 1 plus lambda j. You will get also another statistics here which is Hotelling-Lawley that trace, Hotelling-Lawley's trace, another one. That what is Hotelling lawless stress? Hotelling lawless stress is H, which is trace of R E inverse. This one is nothing but lambda j, j equal to 1 to S. There is another statistics which is known as Roy's greatest root. Roy's greatest root G. So, that G is taken only the first eigenvalue, this one. So, all software including SPSS, SAS, they report all those statistics. So, now what is this? You please understand, under H0 these statistics are developed. So, if that means most of the time we will find out that F distribution. Now, if this value is more than or equal to the cutoff value from F distribution. So, what you will do then? In that case, you reject the null hypothesis. That means the set of x variables m in number, what you have rejected, that is not correct. Now, if I consider m equal to 1, that means individual variables at a time you are testing. So, for every variable you test and then see that whether it is contributing or not. Like in ANOVA case, individual variable SS you have identified. So, with this I want to go to the example. This is the Citizen data. So, intercept, see Pillai's trace, Wills lambda, Hotelling trace, Roy's largest root, all those values are computed, their F test is taken and then significance level is very high. That means intercept is there, it is contributing. Absenteeism similarly, is it significant? Not. That 5% level it is not significant, but little more than 10% level it is significant. Now, you can drop this variable if you think so, but if you think so, then on 10% level it is required, fine. Then you say breakdown for every stress. Interestingly, everyone, Pillai, Will, Clauding T square, everyone is giving the probability level almost equal, but the value is differing and the degree of freedom will remain same, error degree of freedom also remains same, and this is the case. So, what is in nutshell what we are saying? We are saying here that you are going for model adequacy test by similar F test like in case of multiple regression, that ANOVA, but here also you are doing this and you are finding out that yes, some of the variables are contributing, so multivariate regression is required. Now, go to the next one. So, this is the your total sum of squares under that profit under sales, and you see R square like univariate R square, that multiple regression R square. For first one it is 0.924, for the second one, that means for profit 92%, for your breakdown, not breakdown, this is sales 86.6%. Okay. And also you have tested the significance level here for different intercept, for absenteeism, for breakdown, getting me, and their significance level, everything is tested. Once you accept this, you have to go for diagnostics similar to your MLR. This diagnostics is required, and almost all the software they give you this type of plots. These plots are basically, I say, residual plots. Okay. Now, see the residual plots. So, observed versus predicted, it should be straight line linear. Now, observed versus, if you see observed versus, this one is this is observed, predicted, fine. Now, if you go by residuals versus predicted or residuals versus observed, that should not give any trend, it should be random, it is coming like this. Okay. So, predicted versus residuals also, that should also become random. So, this for profit this is the case, for sales also similar thing we are getting, and in fact from this figure you are not getting any unusual observation. In summary, when you go for MBLR, you see that when you have more than one dB, both the more than 1 dB and all the dBs they occur simultaneously. Then IVs are same, means independent variable are same affecting different dBs. Estimation, this is the condition when you will go for this. The multivariate normality, that covariant structure equal and other things, that assumptions you have to test. Then estimation, from estimation point of view, estimation similar to MLR. Model adequacy test is complex because you are going for likelihood ratio test, and there are different tests identified, that Pillai stress, Willis lambda, Roy's greatest root, and then Hotelling-Lawley, all those tests are there. Several multivariate tests, that is why this is used. IV should be truly independent. Other assumptions also equally important, does not give much advantage over MLR, but protect against error handling. So, if you go separately for regression estimate point of view, no problem, but adequacy test point of view there will be problem if you go for separate MLR, getting me. So, this is the advantage, and I think when you have multiple y variables and you are sure that they are following, you are able to prove that assumptions are not violated or reasonably following, then what you have to do, it is better you go for MBLR, multivariate regression first, and then you test through different tests, you are finding out yes these are contributing, then you will, if you go for single MLR, that means multiple linear regression instead of MBLR, absolutely no problem. It is similar to that ANOVA and that analogous is MANOVA. You must go for MANOVA when you have more than one dependent response variable, and then you see that collectively they are affecting or not. If not, go for ANOVA, no problem. So, similarly MBLR and this. So, this suppose this MANOVA and MBLR, all those things comes under general linear model. If you go to SPSS or SAS, there will be one link GLM. Okay. Any question? Thank you very much. Next class we will discuss PCA, principal component analysis. Okay.